Hello, welcome to another session on embedded system design. In this session, we will discuss about the what is embedded system, what are the different types of embedded system, and related concepts. First, let's look at what is an embedded system. An embedded system is defined as a combination of computer hardware and software designed for a specific function. When we say a specific function, it can be a single application or a set of applications. We use embedded system in variety of application. You can see a picture in which various applications are shown, starting with from domestic applications, audiovisual equipment, gaming consoles, telecommunication equipments, medical devices, cars, vehicles, motion sensors, and manufacturing equipment. However, this is not an exhaustive list. They can be used again in medical equipments, space equipments, marine equipments, and lot of applications will be there for an embedded system. An embedded system need not always be an independent system. It can also be a part of a bigger system. So we see embedded systems starting from simple smart watches or electronic toys to a most complicated systems like cruise control or missile control systems or satellite systems, gateways of the network, all are comes under embedded system. So now we'll see how these embedded systems are different from general computers. If we observe the differences between a computer and an embedded system based on a different category or a parameters, we can see a computer is a combination of hardware and a software resource which integrate together and provides various functionalities to the user. Whereas an embedded system or embedded device is a part of integrated system which is formed as a combination of computer hardware and software for a specific function. As I said, in a computer, the software which is there in the hardware is put after the design of the hardware. It is not embedded into the hardware while development cycle of the system itself. Later the software can be installed, like we purchase a computer and later we decide whether to work on a Linux platform or a Unix platform or a Windows platform, which softwares to be used. All those things will be decided later by the user. Whereas in embedded system, the software is not decided by the end user, rather that will be an embedded in the equipment while development of the system itself. That is, if you take a mobile, the software in the mobile comes with the mobile itself. However, it can be upgraded later, but the OS itself cannot be modified or changed. Or you can consider a washing machine, which comes with the software in that, which cannot be changed. Microwave comes with the software inside, which cannot be changed. Like that, any electronic device or a gadgets what we see around, there will be many gadgets which comes with the software within them. So such systems are called embedded systems or embedded devices. Next, if we consider human interaction, then a computer always needs a human interaction and tell what tasks to be performed. We have to tell the computer. Whereas embedded system may or may not need a human interface. Even without a human interface, it keeps on executing certain functions. It is an autonomous system which works by itself. In some cases, it repairs by itself as well. If you see an ATM, whether any user is there or no, but still ATM is working. It is executing something. However, whenever user interacts with the machine, the way it operates will change. Again, it will go back to its original state after the completion of the transaction. Like that, in embedded system, human interface may be there or may not be there, but still it will execute something. Then the purpose of a computer can be reprogrammed for a different purposes depending on what applications to be developed on that. But embedded systems are designed for a specific applications or a set of applications. We cannot reprogram it to entirely a different set of application, which is not possible. A slight modifications or a configurations, what we call, that is allowed, but an entire different set of applications cannot be implemented using a particular device. It can be used only for the applications for which it is designed. If we talk about power consumption, computer needs more operational power than embedded devices. We can see that a computer is mostly it is connected to an AC source and it's continuously supplied with the power. However, laptops can be operated on a battery backup, but still they consume a lot of power. Hardly the backup may be in terms of hours. Whereas in embedded system, the operational power is so less that some of the embedded systems will run on a battery backup for years and in some cases decades. So embedded system uses very less power. However, they can also be recharged to operate, especially if any embedded system is put as a part of a bigger system, critical systems. They are expected to work without any human intervention for a very long time. Then if we talk about complexity, obviously the computers are more complex machines because they will be very flexible and they can work on a different purposes. Whereas embedded system complexity depends on the application for which it is developed. As already we discussed that starting from a simple electronic toy cars or smart watches, which are very simple embedded system, to you can consider very complex systems like cruise control systems or a gateway systems, all or network control systems. All these are quite complicated systems. So the complexity of an embedded system depends on the application. If we talk about memory requirement, the storage memory in a computer is very large, and as well as a runtime memory can be sufficiently large and it can be scaled. But embedded systems are memory optimized. They need to operate with as minimum memory as possible. So it will have a very limited amount of memory and it can be programmed only within that. Then if we talk about flexibility, computers are usually flexible as it can operate for different platform and different softwares. But in that case, embedded devices are quite rigid. They are operated on only specific platform or a software for which it is designed. Then if we talk about data security, computers are less secure due to continuous human interaction. So data may be corrupted or it can be stored also. So the data security is not very high in case of computers. Whereas in embedded system, the data security is very high. Data can be secured for a very long time as no user will interact with the systems most of the time. So data will be secured and it can be encrypted and transmitted to only authorized persons. Then portability. Computers are less portable due to their bulky size and a heavy weight. However, laptops are portable, but still they are quite heavy. They weigh in terms of kgs. Whereas Embedded devices are very small and lightweight. Not all, but there are embedded systems which are very small in size and very light in weight. So portability is one advantage towards the embedded devices. Then if we talk about scalability, in terms of size of memory and peripherals, computers are quite scalable. If you want, anytime we can increase the memory or decrease the memory of a computer system. But that is not a case in embedded systems. Once the memory is decided during the development, then it cannot be changed later. Then upgradability. So computers are easily upgradable in terms of both hardware and software. We can keep upgrading them. Hardware also can be replaced to higher versions. But in embedded devices, we don't have that flexibility to upgrade them. Only they are upgradable in terms of software, in some cases that too with a specific set of softwares. Otherwise, hardware we cannot upgrade. As far as maintainability is concerned, computers requires a frequent maintenance, whereas embedded systems hardly requires a maintenance. So these are some differences and comparisons of computer with a embedded system. Now we will see how an embedded systems are classified. So we can classify embedded system in many ways based on their power consumption, based on their real-time constraints, execution times. Like that, we can keep on classifying embedded system using the different parameters. But here a most generic classification is given in terms of complexity. So based on complexity, the systems can be classified into three categories: small scale embedded systems, medium scale embedded systems, and sophisticated embedded systems. So in a small scale embedded system, we use a microcontroller, which is usually of 8 or 16 bits. Medium scale, we go to 32, up to 32 bits. Whereas in sophisticated, multiple microcontrollers can be part of a single system, and each controller might be of a different bits of operation. So it's a very complex system. So memory availability, small scale will have hardly bytes or a kilobytes of memory. Whereas in the medium scale, it can go up to MBs or a GBs. Whereas sophisticated systems needs an unlimited memory. When I say unlimited memory, it is not infinite. There will not be any memory constraints while development of the system or design of the system. Whatever the memory is required, that will be used there. There is no restrictions as such. Similarly, even in the case of power, the small scale will have a very limited power. Medium scale systems also have a limited power, but with the backup, because they may lead to certain financial or losses. So big backup will be provided to them. Whereas sophisticated systems have to be continuously supplied with the power, either a AC mains or a battery backup, whatever the source may be. But those systems have to be continuously given power, failing to which that may lead to a catastrophic effects or a human loss. So usually sophisticated system will have a continuous power while operation. Then complexity. So small scale will have a lowest complexity, medium will have a moderate or a medium complexity, and sophisticated are the most complex or a highly complex systems. So while programming these systems, usually small scale we use assembly language program or a C or a C++. Whereas in a medium scale, we can use C, C++, Java, Python. There are many other languages which can be used. Whereas in the case of sophisticated systems, along with the available languages, there is a possibility that an exclusive compiler itself is designed for that particular system. For the security reasons, it may not use the existing or a commercial programming languages. Rather, a separate language or a compiler itself is developed for those systems, especially in a critical system or a security systems. It is very important that language integrity has to be maintained. Then as far as operating systems are concerned, usually small scale system does not need operating system. Even in a medium scale, it is optional most of the time. But sophisticated system need an operating system which is developed for a particular application, or existing OS is modified as per the requirement. A special software is developed. Then as far as the applications are concerned, small scale systems are used in electronic ties, digital watches, or simple MP3 players. All these small electronic gadgets what we see, those will be a small scale embedded systems, remote controls, all those things. Whereas in case of medium scale, we can talk about ATM machines or a chocolate vending machines or a video games. Like that, we have some medium scale systems. Even here we can have a washing machine or a digital TVs. So many medium scale systems we use in our daily life as well. And when we come to our sophisticated systems, they are very complex, like cruise control systems, gateways, network systems, or the missile control systems. When I say cruise control, it can be a aircraft control system as well. So all these things can be used, and all these things are classified, all these equipments or devices or systems are classified as sophisticated embedded systems. If we have to see an examples, for a small scale system, we use 8051 or PIC microcontrollers. They are the examples for the microcontrollers which will be used in that particular category of the embedded systems. In a medium scale, we usually use ARM based systems, or even we can have power PCs of IBM. Then in sophisticated, we use usually a system on chip, or a parallel processing concept, or a multi-processing concept. So as they are very complex, we may need more than one processing units. Next, we talk about two types of instruction architecture which are used in embedded system, that is RISC and CISC machines. RISC is a reduced instruction set, computer or a code, and CISC is a complex instruction set, computer or a code. In some references you see it as a computer, in some references you may see it as a code. Both are accepted. So as the name itself says, a reduced instruction set has very limited instructions and simple instructions. So as the very few instructions are there, the decoder circuit for those instruction set is also simple. Whereas in case of CISC, the decoder circuit becomes very complex, as there is a large set of instructions which are to be decoded. And again, if we talk about length of an instruction in terms of memory they consume, most of the instructions in RISC are fixed in length, or usually they take a single byte of memory. Whereas in case of CISC, each instruction may take a different amount of memory for storage. Similarly, even in case of execution, RISC instructions usually take only one clock cycle or the fixed number of clock cycles for all the instructions. Whereas in case of CISC, the number of clock cycles taken by the instruction varies to a very large extent. Starting from single machine cycle to a 3 to 4 machine cycle instructions can be part of a instruction set. As RISC are very simple instructions and of a fixed size length, both in terms of memory and clock cycles, they are fast execution or less time they consume for the execution. Whereas CISC instruction will take more time for the execution, as they are quite complex. RISC are less code density. What it means is more number of instructions are required to achieve a specific task. Whereas in a CISC, only few instructions can achieve the same task. So the code will be very small in case of CISC. So code density will be better in CISC compared to RISC. For example, if we talk about, say, multiplication operations, a RISC may not provide a direct multiplication instruction. Rather, the multiplication might have to be implemented using a repetitive addition or a shift and add method. Whereas in case of the CISC instruction set, most of the instructions do provide a direct instruction for multiplication and division and other operations. Then, if we talk about pipelining, the implementation of pipelining is easier in RISC architecture as the length of the instruction is fixed in terms of machine cycles. Whereas it becomes complicated in case of CISC architecture. But however, it doesn't mean that we cannot have a pipeline in a CISC computers. We can still have, but only the implementation becomes complex. It is not impossible to have a pipelining structure in a CISC architecture. We can still have it. The complexity is increased only because of the variable length of the execution clock cycles of instructions. Then in case of the RISC, usually we have an orthogonal register set and CISC gives non-orthogonal register set. Orthogonal register set is a one in which all registers can be operated with all instructions in all addressing modes available. Whereas a non-orthogonal register set, there is a restrictions on the registers which can be used for a particular operation or with a particular instruction, and only a selected registers can be used in a selected addressing modes. Addressing modes are basically a different methods of accessing a data from memory or other registers. In simple words, it's a different method of accessing a data that we call the addressing modes. Most of the time, CISC architecture provides an accumulator which performs most of the operations, or it is mandatory to have that accumulator as a part of instruction as an operand for most of the operations. Whereas in case of orthogonal register set, there is no concept of accumulator. Any register can be used for any instructions in any addressing modes. So there is no restrictions as such. However, in both the cases, whether it is a RISC or a CISC, some registers can have a multiple functions associated with them. So programmer has to take care which register to be used for which operations. Then if we talk about general purpose registers, so RISC will provide a large set of general purpose registers, whereas CISC has a very limited set of GPRs or general purpose registers. However, the special function registers depends on the microcontroller which is selected, irrespective of whether a CISC or a RISC. But general purpose registers are usually large in case of RISC and limited in case of CISC. So if we talk about an examples, then ARM and MSP 430 are the two examples of RISC. However, they are not the only CISC character. There are many others. It's just an examples. And for a CISC, if we see examples, it can be 8051 or a PIC microcontrollers. They come under the CISC instruction set architecture. Then we talk about two type of memory architecture. One is von Neumann, another one is a Harvard architecture. So these are the two different types of memories and memory accessibilities. Each one has its own advantage and disadvantage. So it depends on the application which is to be chosen. In case of von Neumann, if we see a block diagram, there is a common address space for both data and program. And there's a common set of bus, that is address and data bus, which are used to access the information from memory address space. At the same time, if we observe the block diagram of a Harvard architecture, there are two different address spaces provided for program and data memories. They're separate. And we can also observe that the address bus are also different. There are different data bus. There are independent address buses. So address and data buses are independent for both program and data in case of Harvard architecture. In case of von Neumann architecture, they are common. There is only one address bus and there is only one data bus, which is used to access both data as well as program. Next, if we see a comparison between von Neumann and Harvard, simple or a same physical memory address is used for both instruction and data in case of von Neumann, as we see in the block diagram. Whereas in case of a Harvard architecture, separate physical memory address will be there for instruction and data. Again, in von Neumann, there is common bus for data and instruction to transfer from memory to a CPU. Whereas in case of Harvard, we have a separate address and data bus to access respective information. We have a separate address bus and data bus for the instructions, and we have a separate address bus and data bus for the data memory. So in case of von Neumann, separate clock cycles are required for a same instruction, because one clock cycle is required to read the instruction and another clock cycle is required to read the operand, because they cannot be accessed simultaneously. Whereas in case of Harvard, an instruction is executed in a single cycle, or instruction can be executed in a single cycle, because instruction and data both can be accessed simultaneously. They provide a separate bus architecture for both of them, so they can be operated independently and accessed simultaneously. That's what the next point says. Whereas, as the separate address bus is provided in a Harvard, but in the von Neumann we have a common address and data bus, the address width of both program and data must be same. Whereas in case of Harvard, we can have a separate address width for program and data memory. If we need a large amount of data to be stored, then data address bus can be increased. If you have a large program with the minimal data, then program memory address can be increased. For example, if a system is developed which is operating on a sensor-based system, which is capturing a certain data from the variety of sensors, and based on the values of the sensors or the threshold values, certain actuator has to be driven. Here we can see that program is quite large, but data on which it operates is very, very small amount of data. Hardly bytes of data it will be using for processing. But most of the job what it does is execution of the program or the process of the program. Whereas at the same time, if you observe image processing or a signal processing applications, the program is very small compared to a data on which it is operating. There's a huge amount of data, KBs, MBs of data might be there, and that entire data has to be operated by one algorithm or a small code. The same code will be executing on all the data sets available. So in case of such things, the data on which the system is operating is very large, but the program is very small. So program memory size can be less, and data memory size can be more. As there is a common integrated chip in case of von Neumann for both program and data memory, obviously the cost and size will reduce, whereas in case of Harvard, it is much costlier compared to von Neumann. As we already discussed, CPU cannot access instruction and read-write at the same time, whereas in case of Harvard, instructions and read-write operations of data can happen simultaneously. Von Neumann is used in a personal computers and the small computers, and usually the Harvard will be used in microcontrollers and signal processing operations. As the only single IC is there for entire memory, the overall total implementation footprint is less in case of von Neumann, whereas we need two separate ICs in case of a Harvard, so implementation footprint is more. So with this, we go ahead with the big and little endianness. Endianness is basically a way in which the data is stored in the memory. So there are two methods in which the data can be stored in the memory. One is big endian, another one is a little endian. As I said, endian is a method in which the data is stored in the memory. If you observe in the book Big Endian, the least significant byte is stored at a higher address and most significant byte is stored at a lower address. So if we see an address starting with the A, then next address is A plus 1, next is A plus 2 and next is A plus 3. At the address A, that's the least address, a most significant byte of a data is stored. And at a higher address, a least significant byte is stored. That is A plus 3 is the highest address. There, least significant byte, that is 0D, is stored. I repeat, the most significant byte is stored first at a lower address, and then sequentially the next bytes keep storing in the next consecutive memory locations, and the least significant byte is stored at a highest address in case of big endian. Whereas in case of little endian, least significant byte is stored at a least memory, that is starting at A. First least significant byte is stored, then subsequently next byte of information will be stored. A plus 1 will store the 0C, A plus 2 will store 0B, and A plus 3 will store the most significant byte of the information. This type of storage applicable both is for a 16-bit data, 32-bit data or 64-bit data. Depending on the size of the data, the number of memory locations what it consumes will vary. Whereas in case of memory, each memory location will be of 8 byte. That is not going to change. That's going to be fixed. If you want to store 16-bit data, then we need 2 memory locations. If we need to store 32-bit data, then we need 4 memory locations. For that reason, the big and little endians are defined to identify how the data are stored, whether the least significant byte is stored first or the most significant byte is stored first. In case of big endian, most significant byte is stored first. In case of little endian, least significant byte is stored first. Then sequentially at a highest memory, least significant byte is stored in case of big endian, most significant byte is stored in case of little endian. With this, we come to end of this session. Thank you, friends. See you again in the next session.